Periodic table families and trends in a nutshell. So we're going to discuss the periodic table, some data you can gather from it, and what periodic trends are and how you can determine them. First off, the periodic tables are organized according to either groups or families. So groups or families are going this way. They're columns. They're vertical columns in the periodic table. So there are approximately 8 different groups or families in the periodic table. Rows are left to right. So these are your rows. These are called your periods. So we have families or groups going up and down, and we have periods left to right. Now, which one is more significant? The groups and families. And the reason is because members of the same family have similar characteristics. Now, this will make them important. They actually have names for these families. And we're going to go through them. So first group is alkaline metals. Note it does not include hydrogen. It's in the family because of its properties, but it is not an alkaline metal because it's not a metal. It has to be a metal to be an alkaline metal. So we're going to ignore that. But everything else in this first group is called the alkaline metal family. That's all these. Alkaline earth metal right next door. That's all group 2A. And there's 2 different systems for naming it. 1, 2, all the way to 18, or the A and B system. The A and B system basically separates representative elements from everything else. The main thing you need to know is that they represent the same thing. If I say group 1A, same thing as saying group 1. 2A, same thing as saying group 2. Where it gets weird is when we get to group 13, which is actually group 3A. So let's continue going to families. So these middle ones over here, these are all called transition metals. The next family name we get to is the halogens, which is over here. There's a family name for oxygens group as well. It's called the chalcogens, but we're not going to discuss that too much. Halogens are group 7A or 17. Noble gases are group 8A or 18. What they have in common is their valence electrons. They have the same number of electrons in their outermost shell. So it turns out that group 1A has exactly 1 valence electron. Group 2A has 2 valence electrons in the outermost shell. So if you think of the Bohr model, you know how you draw your rings. The last ring is your valence shell. The number of electrons there is what these numbers represent. So alkalides have 1 electron there. Alkaline earth has 2. We're going to skip the transition metals because they're kind of weird. And group 3A has 3. 4A has 4. Do you see a pattern? So that's why the A-B system is really important versus the 13, 14, 15. Because if you look at terms of group 3A, 4A, 5, 6, 7, 8A, that's actually how many valence electrons you have. 5, 6, 7, 8. Also on the periodic table, we have the staircase. What the staircase does is separates the metals, which are on the left, from the non-metals, which are on the right. Right on the staircase, we have what's called semi-metals or metalloids, and that includes boron, silicon, germanium, arsenic, antimony, tellurium. Polonium acetate really depends on the source. Some say it isn't, some say it is. Let's include both of them, but just be aware, some sources say that polonium isn't, some sources say acetylene isn't. The really ones you have to worry about is the other ones. As far as how do you remember these, it's everything on the staircase except aluminum. And realistically, let's make this easier for ourselves. Let's call it everything except alpo, everything except aluminum and polonium. So we're going to ignore polonium. We're not going to consider it because some sources say it isn't, so we're just going to ignore it. And it's easy to remember alpo. So everything on the staircase except alpo is a semi-metal or metalloid. On the bottom, we have the lanthanides and actinides. The only thing you need to know about them, they're actually originating from here. They pulled it out from these locations. If you look at the atomic number, you see how this goes 56, 57, and 58, not 57, 72. They actually pulled this from this period, so it's a period 6 element. They pulled this from period 7, so it's a period 7 element. Why did they do that? To make it simpler to see a periodic table. Otherwise, it's going to be way too wide. So that's the origin of that. So valence electrons, number of electrons in the shell versus the nucleus, and we discussed how you can determine those. Families or groups have similar chemical and physical properties due to the fact they have similar valence electrons. That's why they're called a family. Same number of valence electrons means same type of reactivity as a chemical. That's important. And once again, metals are on the left. You see all the green things are metals, metalloids. on the staircase. You can see here they counted PO as a metalloid, but it really depends on your source. So we're not going to analyze that too much, and we're not going to test on that either. So whether you consider it or not doesn't really matter. And then we have our nonmetals on the right: noble gases, halogens, alkaline earth, alkaline metals. You can see the majority of the periodic table is actually consisting of metals. That's important to note. All right, trends in the periodic table. Here are the rules we're going to use to understand the trends. First rule: electrons are attracted to the protons in the nucleus. Common sense, right? Opposites attract. As part of that, we're going to emphasize that the closer the electron is to the nucleus, the greater the attraction. So electrons in the first shell are going to have greater attraction than ones in the second and the third, and so on. So closer it is, greater attraction. That's one thing you need to remember. Other thing, more protons means greater attraction. So if you're comparing two elements, the one that has more protons is going to have a greater attraction towards nucleus. Why? The more protons you have, the more attractive that element is, the prettier it is. Imagine protons as positive attributes for an element. The more positives it has, the more the electrons want to get closer to it, the greater the attraction. So when you look in the periodic table, you notice the atomic number goes up as you go left to right. It increases as you go left to right, which means that you're adding more protons. So what do you think happens to the attraction of the nucleus to the electrons as you go left to right? That's right, it increases. Why? More protons means more attraction. The other rule we're going to remember is more shells means bigger size. Common sense, right? If I draw a circle and then I draw another shell and then another shell, each time I draw a shell, it gets bigger and bigger. That's what the atom is. As you add more shells, you go down a grouping. And as you may have not noticed, the periods, there's a total of 7 periods, right? 3, 4, 5. That represents how many shells the element has. So elements in period 1 have 1 shell. Elements in period 2 have 2 shells. 3 has 3 shells, so on and so forth. So for example, lithium, which is in the second period, that's a nucleus. 1, 2 shells. Why? Because it has 2 electrons in, it has 2 electrons in this shell, and then 1 more electron in the third shell. 3 electrons total matches what we just hypothesized. So you could kind of figure out how many shells an element's supposed to have just by looking at what period it's in. Really simple. And as you add more shells, the atom gets bigger. All right, so let's look at the atomic size. Notice how the atom gets smaller. As you go left to right, the number gets smaller. This is the radius of the atom. So why does it get smaller? Well, we established that earlier. Protons. Protons means greater attraction. So if there's more attraction toward the nucleus, what the electron is going to want to do? Get closer to it. They get drawn in. And that's why the size of the atom gets smaller. So atomic size of the atom gets smaller as you go left to right, and the reason for it is because you're adding more protons. Just remember PP. More protons in a period, which means greater attraction. So if you're trying to explain why the atom is going to get smaller, you're going to think PP, because there's more protons in a period. The more protons in a period, the smaller the atom becomes. So the biggest atoms are actually on the left side of the periodic table. Why? Less protons. As you go down, what happens to the size? Notice it gets bigger. Number gets bigger. Why does it get bigger? More shells. It's really simple. Talking about elements in the same period, you look at the protons, you look at the elements in the same family or group, you count your shells, which is basically your period number, right? You could tell cesium, for example, has 6 shells. How do I know this? It's in period 6. All right. Size of metal atoms and ions. A positive ion has lost of valence electrons. So now that we've talked about neutral atoms, let's talk about ions. Remember, cations lost an electron. What happens to their size? Look at this. It's about half the size. Why? Because when lithium loses 1 electron, here's your lithium again. Here's your 2 electrons. When it loses 1 electron, it loses the whole ring. So now it only has 1 ring instead of the original 2. So that's why it gets smaller in size. So it's smaller, about half the size in its corresponding metal atom, since it loses the whole shell. Negative ion, on the other hand, gains an electron. Now, before you get confused on this, so let's look at fluorine. We're going to ignore the protons and the neutrons, which are 9 and 10, but that doesn't matter. So how many electrons does fluorine originally have? It's going to have originally a total of 9 electrons. Why? It's neutral. That's why. atomic number is your proton, which is your electron. So 1, 2, 3, 4, 5, 6, 7. That's a total of 9 electrons. So what happens when you become an anion? You add one more electron. So you're like, why does it get bigger? First off, you want to note the electrons added to the same shell. You're not adding an extra ring and adding an electron in it. Don't make that mistake. What happens is that because this electron goes in here, all the other electrons repel away from it. So what happens to your side? It gets bigger. Why does it get bigger? Because electrons repel against each other. So if you add one more electron, all the other electrons are going to push away from it, and your atom's going to get bigger. So anions are bigger than the neutral atom. Cations are smaller, anions are bigger, twice the size. All right, so let's take a look at some trends. Ionization energy is the energy you need to remove an electron. So it increases as you go left to right because of more protons. So as you go left to right, remember what we said? More protons, more attraction. The more attracted the nucleus to the electron is, the harder it is to remove it. So as you add more protons, your ionization energy increases. So that's why ionization energy increases as you go left to right. Down a group, what happens? Remember, the atom gets bigger and bigger and bigger. You're only going to be removing valence electrons. So electrons in the first shell from the nucleus. So as you go down, that electron's further and further away from the nucleus. So what does that mean? Less attraction. So what does that mean? Easier to remove. So it decreases down a group, not increases. So as you look down a group, ionization energy decreases. Why? Because there's less attraction to the nucleus. The less attraction there is, the easier it is to remove the electron. Because that's all it is. The energy needs to remove an electron. So there's less attraction, you're going to have easier time removing it. All right, let's take a look at electronegativity. This is how cute the atom is. The more electronegative it is, the cuter it is, which means it attracts electrons more to itself. So how does it increase? Same as ionization energy, increases you go left to right. Why? Because your cutest elements are on the right side of the periodic table. Why? They have the most protons. As you go down a group, what happens to electronegativity? It decreases. Same reason as ionization energy. There's less attraction to the outermost electron because the atom gets bigger and bigger. So that valence electron is a lot further from the nucleus, so it's easier to remove. One thing you do want to note, though, noble gases have no electronegativity. They're not cute. They're ugly elements. Electronegativity, all these are 0. The most electronegative element then becomes fluorine, which is about 4.0. That's the highest value. The lowest one is going to be the noble gases. All right, so let's try some key questions. Which of the following pairs predict which atom had the higher first ionization energy? So you look at magnesium and sodium in the periodic table. Sodium has 11 protons, magnesium has 12. Because magnesium has one more proton, guess what that means? Greater attraction to the nucleus, higher ionization energy. So the correct answer for that one, let me show you all of them, is going to be magnesium. Why? One more proton. That's all it takes. S and O. S and O are both in the same family. So if you look at it, it's in group 6A. Oxygen is directly above sulfur. So that means sulfur has one more shell of electrons than oxygen. Because of that, sulfur is going to have a lower ionization energy, which means the answer to this question is oxygen, because it has fewer shells. The less shells you have, the greater ionization energy. Calcium and barium, they're also in the same family. Which one's higher up? Calcium. So it's going to have a higher ionization energy. Once again, the higher it is, the fewer shells it has, the higher the ionization energy it is. Chlorine and iodine, also in the same family. Chlorine's above iodine, group 7A. So chlorine's going to have a higher ionization energy. Sodium and aluminum, they're in the same period. Aluminum has more protons. More protons means more attraction, which means higher ionization energy. And then lastly, selenium and bromine, also in the same period. Bromine has more protons. Remember, the more protons you have, the greater attraction to the nucleus, and the higher the ionization energy. So that was the periodic table and periodic trends.